this stream, we're going to kind of do a brief overview here, and then go into practice questions, Q&A, whatever you guys feel like asking questions about. That's what we can do. So we're going to do some properties, some definitions, common terms that we need to know. Some of these you may have heard of before. Some of these are brand new for AP. Just kind of depending on what background you've got in physics so far. Then we're going to go into the relationships, do a couple of simulations to talk about how are these things related to each other in experimental sense, and then hit the math, hit the equations, and then onto some practice questions, some multiple choice and some free response. In general, I think in the past 4 years of the AP exams, there's always been a free response question on waves somehow on there. So something to think about. This is, even though waves is a very small topic as far as the percentage on the, I think it's only like 6% of the exam. But the free response section, there's almost always a question on waves somehow in those free response questions. All right, so let's get into defining some terms. All right, so on here we have the anatomy of a wave. And pretty much here we have all the different terms that you might need to know about. We've got terms like crest, trough. So crest being a high point of a wave, trough being the low point of a wave. We've got a wavelength, literally the length of a wave, which is measured from either crest to crest, or trough to trough, or 0 point, one full up and down to the next 0 point. Okay. Now, in this case, this wave is transverse, and that just means it vibrates up and down as the wave goes left and right. This would be if you're making a wave on a rope, or you're watching an ocean wave, or other things like that, where if you can trace it, it goes up and down, up and down, up and down as the wave goes to the left or to the right. We're talking about a transverse wave. There's another kind of wave we'll get to in a second called a longitudinal wave. It's basically the same terms, just it's going to look a little different because that is squishing and expanding as the wave moves through. Okay, so we've got crest, trough, wavelength. Amplitude is our next one. Amplitude is the height of the wave, how tall it is or how short it is. And that is measured from this 0 line, from this central line here, either above or below. It should be symmetrical, so it doesn't really matter which one you choose. Height of the wave, how tall or how short it is. And the last term over here is frequency. Frequency is how many waves come by every second. So this, if I have a wave come by 5 times in 5 seconds, it is 1 hertz. If it's 5 times in 10 seconds, it's half a hertz. If it's 500 times in a second, it's 500 hertz. How many waves we have going by a point at any given instance in time. Okay. Now, let's get on to some relationship stuff. So as far as your reference tables are concerned, they really only give you 3 things: frequency, wavelength, and velocity. So the speed of a wave can be found by taking the frequency and dividing it, or sorry, frequency times wavelength is speed. Your reference tables, for whatever reason, have it solving for wavelength, which is fine. I mean, we can all do the algebra to multiply it over and get V equals F times wavelength, but it's just a choice they have on them. So, well, I am going to mostly, I think all the examples I've taught with, most of the time we find V. You can use it to find F or lambda, it doesn't really matter. They're all fairly interchangeable. The other equation on there is relating frequency period. We did that back when we did the springs and talking about the frequency of the oscillations up and down for a mass on a spring or a pendulum swinging back and forth. But that is simply period is 1 over the frequency, and frequency is 1 over the period. So they are inverses of each other. All right, so now on to a couple of demo, I guess, things. So let me switch something over here. Let me fix this. Ignore my face for a second. Maybe this one first. All right, so this one is looking at an online tone generator. Because some of the questions we need to get to is, okay, what the heck is this frequency thing actually doing versus not doing it. So I'm going to turn on my speakers here. I apologize for any popping and echoing that happens here. But yeah, a tone. This is 290 hertz, and that is the frequency of that note. As we lower the tone, we get a lower pitch. It actually sounds lower to our ears. And in fact, we as humans can hear anywhere from 20 hertz. So this is actually below what human hearing can hear. And we will be able to go up to roughly 20,000 hertz. Sorry about that. So now we're going to ramp this up to 20,000 hertz. Now, I will tell you, at some point in time, I will be able to stop hearing this, but you might still hear it. Our maximum hearing range is depending on our age, and because I'm older than 20, I actually have lost some of that upper hearing range that some of you may still hear. So I'm not going to hold up for very long, but we're just going to ramp up the frequency of this and see what happens. All right. So I'm going to mute the speakers again. Excuse me. So in this case, you could hear that as the frequency got higher, the pitch got higher too. We heard a higher note with the sound. And as we go back down, the frequency we get lower and lower and lower. And this essentially is where we're going to get into talking about musical notes. So each note that you would play on a piano or a clarinet or a saxophone or any musical instrument has a certain frequency to it. And for example, middle C is somewhere around 523 hertz. And that is the middle of the keyboard on there. And that is where we are at. You can go up, these musical notes stop at about 8,000 hertz, which is good because beyond this point, we just start hearing like a high-pitched trill or a whistle or something like that. Kind of tough for us to actually call that music, although you could eventually continue the musical scale all the way up that top part. But anyway, the point I want to bring out right now is frequency is pitch. You hear a higher frequency as a higher pitch, and vice versa. Lower frequency is a lower pitch. Okay, so that was the aside for notes. We're going to come back to that next week because notes and music go together very well. We'll talk about harmonics and some of the fundamental things there. So there's the next one. Okay, so this one is a simulation I like to use with my students in class just to get some ideas of what a wave is, what a wave is not, and what a wave depends on. We also do this with slinkies out in the hallways, but there's something nice about knowing that this will always give you the right results and it won't depend on what we do. Okay, so the first thing we're going to do here is I'm just going to set this up. These would represent a wave or a string or a rope or something like that on there. And I could do a single sort of thing. So we can wiggle this once and we watch they go through. That is a pulse. In fact, here we'll do this as a pulse. A single disturbance. This is not a wave. Okay? Just make this very clear. A wave needs to have multiple disturbances. Okay? So a wave on a beach is not one coming in. It's one after the other, after the other, after the other is why that's a wave. It's an oscillation. Now, everything we're going to be doing in AP will revolve around some sort of periodic oscillation, meaning it happens over and over and over again with the same predictable timing. So in this case, let me change this a little bit here. We're going to make one wave every second. So we're going to set our frequency to 1. This means that this little plunger will go up and down once every second. Okay? And that is our wave. Frequency of 1, period of 1, it goes up and down once every second. Okay? Now in this case, we've got damping turned off. Damping is basically friction for a wave. We don't have to deal with that in AP1 because we're assuming that we have ideal situations and we'll not have to worry about that. We can adjust the amplitude, so I can crank the amplitude down and notice the height of the wave got much smaller. If I crank the amplitude up, we suddenly get much bigger things going on. So up and down, up and down, up and down, bigger height, bigger amplitude. For music and stuff like this, a wave with more amplitude means it sounds louder. So we're talking about a much louder sounding wave. So this would be somebody shouting versus somebody whispering. Okay, so the higher the amplitude, the more energy there is in that wave, and the louder it sounds to us. All right, now, next thing I want to point out is that as this wave goes from the left to the right, as it travels through this material, each of these dots only move up and down, and up and down. These dots are not moving left and right. This is why this wave is called a transverse wave. The particles move transverse, or perpendicular to the direction the wave moves. And most of the waves that we're going to talk about will be drawn as this transverse wave, up and down, up and down, up and down. Okay. And we'll pause it right about there. Maybe. Okay, click on the right thing, pause it. There you go. Let's pause this. So right now we have our wavelength from this green dot over to this one. We've got our amplitude underneath, and our frequency is told to us right now. Okay, we're going to crank up the frequency here now, and notice that as the frequency happens, let's double. Let's go to 2. So now, as we've doubled the frequency, notice that our wavelength has shrunk. It used to be from here to about here. Now it's this dot to this dot. It is, in fact, it's half as much in there. So this wavelength got smaller when the frequency got higher. And that should make sense, because if we have this much space to make a wave, normally, and I make a wave twice as fast, then I have to get 2 things in the same distance, half as much for each one, or a third as much, or a fourth as much, or whatever we're looking at here, going through. So we'll let this run, and again, we crank our frequency up really high. High frequency, this is the higher pitch. The wave happens more often. It is squished up, smaller wavelength, and higher frequency. Okay, but what's interesting here, and we can actually do the math out with a ruler. This is 3 hertz. My wavelength is approximately 2 centimeters, 0 here to 2 here. So that is my speed of this wave is about 6 meters per second, or 6 centimeters per second. I'm going to turn the frequency down to 2. And we should see that now my wavelength changed. It is now about 3 centimeters, which means my speed is now 3 times 2, 6 centimeters per second. The speed didn't change. It was the same when we had a high frequency as when we have a low frequency. So let's try 1. All right, so in this case, can I get it? Yeah, my wavelength is somewhere around, and again, this is not the best way to measure it, somewhere around 6 centimeters. So we were able to get 6 times 1, or still 6 centimeters per second. The speed of the wave, the velocity of the wave, doesn't change when you change the frequency or the wavelength, because the velocity doesn't depend on the frequency or the wavelength. And this may be a little counterintuitive, but what it depends on is actually this tension value down here. I always tell my kids it depends on the material we're using. And if that material is more dense, can transmit better, these disturbances, these vibrations, it is a faster wave. Right? The classic example is air. Sound waves go through air at about 340 meters per second. Sound waves go through a piece of steel, like metal train track sort of stuff, at around 1,000 meters per second. That's why you hear stories, or maybe I hear stories, I'm not sure if you do, of people listening. Like back in the 1800s, how can you tell a train was coming? Well, you put your ear to the rail and you listen, because the sound from the train is transmitted to your ear through the rails a lot faster than it does through the air. Okay, so if I want to change the speed of this wave, I'm going to change the tension. And let's put it on low. Let's just see what happens here. Okay, so notice this thing is now much different. By changing this tension down super low, my wavelength went from being 6 centimeters to now only being, well, 1.5, maybe, somewhere in there. So I went from having a speed of 6 meters per second, or 6 centimeters per second, to about 1.5 centimeters per second. That is a huge difference by just changing the tension in the spring. If I put it somewhere in the middle, I'll probably get some number that is somewhere between 6 and 1.5. And it looks like at the middle setting, we are 3 3/4, 3.7, 3.8 centimeters per second. So the higher the tension in something, or the denser the material, the faster waves travel through it. If you guys remember Earth science, P waves and S waves, there's a reason P waves come first, is because they are allowed to travel through denser materials. S waves are not, because of the way they're moving. And that gives us a different speed of the wave and a different outcome. All right, so that's this one. So waves must be repeated oscillations. We've got wavelength top to top, and as frequency goes up, wavelength goes down, as long as you're keeping the material, the tension in the string, or other something that's the same, the velocity won't change. If you change the tension or change the material, the velocity definitely will change, and then you got to go and recalculate all that stuff like that. All right, so this one's done. This one's done. Let me do the last sim here, and we'll go on to some free response questions and stuff like that. The last one I want to show you guys is this. This is a pretty awesome Desmos simulation, put together by a colleague of mine, works in the city of Rochester. But he's an expert at doing these sort of Desmos sort of things. Desmos is really awesome if you need a graphing calculator or just to throw up some data really quickly. But I have no idea how it does this. This is just wonderful. All right, so what this is illustrating are the two different types of waves that you can be asked about on an AP exam. There's transverse, which is the sine wave up and down sort of thing that we've been describing before. But the top part, the longitudinal ones, are kind of different. They're squishing and expanding, and squishing and expanding. So you get these spots where it scrunches up and spots where it spreads out. Now you can still do things like wavelength and frequency and stuff like that. What's the time period between scrunches would give you the period, therefore the frequency. Wavelength you'd measure from one of these lines, then when it's scrunched, to another one when it's scrunched again. So you got to look for patterns in there, and you say, oh, I'm going to go from this most scrunched area to the next most scrunched area. And in fact, these are both showing the same wavelength on here. So we can see we're looking at going from about here to about here. So somewhere we do like 25 and 65 would be 40 units for the wavelength of this. So you've got to scrunch. Let's see, scrunch here, and then scrunch there. Yeah, so somewhere around this 10 and then this 55 range. So it's getting about 45 scrunches in there. This would be a little bit easier to see if it wasn't moving. So let me see if I can pause this time here. Pause. Okay, there we go. We'll go back to the beginning here. That's really good. So in this case, I would find the wavelength by going measuring in this region over to this region. And on the AP exam, they would typically, again, represent these waves as vertical, or these marked as vertical lines, just measure the distance between them when they match up. Okay. Longitudinal waves are actually how sound waves travel. You push on the air molecules and they vibrate back and forth and back and forth and back and forth. You speak, and then they get transmitted that way through the air. You can also do it with a spring. If you pull a slinky back and just kind of twing it, it just disturbance travels downwards and backwards, sideways with it. So it's a forwards and backwards, forwards and backwards, forwards and backwards sort of thing. Just like in the waves on a string simulation, though, none of these particles actually move with the wave. They just vibrate back and forth in place as the wave goes through. The wave itself travels to the right in all these simulations, but each particle just wiggles in place and ends up at the same spot it started at. And that's a pretty big issue with my students. They go to the beach and they see the water come up and come up and come up and come up, and waves wash over them, or the tide comes in or stuff like that. And they get this idea that waves throw a lot of whatever the wave is made of out with it. That's just not true. If I make a wave on a string, the string doesn't fly out of my hand and end up at the other end. If I use a slinky to make a wave, the slinky that I'm holding on to doesn't suddenly disappear and reappear at the other end with that wave. It's not the whole thing travels, it's just the energy travels through it. It's a disturbance going through there. All right. So that being said, let's go back to some notes. Yeah, I want to share that slideshow back up. So again, all this slideshow stuff with the links to all the sims is to be posted on Fiverr, so you can rewatch it and go through and just take a look at all these things if you want to play around with them more. I realize some of you may not have covered waves yet. This is a little bit out of order. This is unit 10 according to the AP, but we're teaching it now because it kind of just works. It's a good transition before we get to rotation stuff to talk about waves, because waves are caused by rotating things, and it's a transition sort of thing. So your teacher may or may not have covered this yet. Even if they haven't, that's fine. Come back, watch it later on in the year for review and stuff like that. That'd be great. Okay. So that being said, let's click through here. All right, so some sample multiple choice questions. If the frequency of a sound wave is doubled, the wavelength ... All right, so we take our frequency, how many times this oscillates, and I make it twice as fast. What happens to the wavelength? Well, the first thing I would do here, if I didn't know, was to take a look at my reference tables and find that equation that talks about velocity, frequency, and wavelength. This one looks really good to use. So if I make F get twice as big, either V changes to become twice as big, or V stays the same and the wavelength becomes half as much. So which one is it in this case? Excuse me. All right, so in this case, they don't mention anything in this question about us changing the material. It's still sound waves traveling through air. It's not going from air into water or anything like that. So all we can say here is if we're not changing the material at all, the speed can't change, which means C and D are both wrong because we're not changing material, therefore we're not changing speed. Okay? And then we go back to our equation. V equals F lambda. If I make F get twice as big and V stays the same, this fraction becomes half as much. So choice A will be our right answer for that case. Okay. Second one. As the sound goes from steel into air, both its speed and its something, either wavelength gets bigger, wavelength gets smaller, frequency gets bigger, or frequency does not change. All right, so in this case, now we are talking about two different materials. So we're going in steel, incredibly dense, incredibly well put together. It's solid. Sound waves travel very fast. Each molecule can bump into the next one super quick. So we are going from a fast material, steel, into a slow material, air. Air being a gas, much more spread out. It takes more time for the molecules to bump into each other to send these sound waves through it. So because of that, we're going from a fast material into a slow material. Its speed better decrease. And only one option on there has decrease as choice. Okay. And it is the wavelength gets smaller. Okay. Going back to our equation here, lambda equals v over f. If v gets smaller, the wavelength gets smaller, and the frequency doesn't actually change. And we saw that in the simulation. Let me go back to that for a second now. Because we took a look at that simulation. Stop sharing. Share the simulation. This one works. Okay. We saw that in this simulation where if we were to change the tension, where is my cursor? Let's go back to the oscillating one. Turn this off. End. Okay. Frequency is 1.5. I change the tension. Notice how the wavelength changes. The wavelength got a lot shorter because I went from fast to slow. The frequency stayed the same. Okay. So because of that, this is where we're going into the idea here of wavelength will get shorter. When speed gets shorter, frequency does not change. It stays the same throughout. Okay. And now if you're going on to take AP2 or some other physics where you're going to be doing optics and mirrors and lenses and stuff like that, that idea also is super important for that topic, where you're go from one material to another, the wavelength changes, the speed changes, but the frequency stays the same. All right, so our best answer for this one is choice B, going from fast material that's dense to slow material that's less dense. Both its speed and its wavelength will decrease. Choice B. Okay, next one. A person vibrating the end of the person vibrating the end of a string sends transverse waves down the string. If the person doubles the rate at which they vibrate the string while keeping the same tension, the speed of the waves do stuff. All right, well, let's look at the first part here. Again, if we are keeping the same tension, that means the speed of the wave stays the same. Changing the tension changes the speed. Changing the density changes the speed. Keeping that stuff the same, the speed does not change. All right, so now we're down between A and B. Either when I increase the frequency, double the rate at which you vibrate the string, going from slow to fast. If you increase the frequency, the speed of the waves is going to get smaller. Should be choice A. All right, and the last one. A vibrating tuning fork sends sound waves into the air surrounding it. So a tuning fork, if you don't know, is basically a musical instrument used for making sure it's on the right pitch. It's a piece of metal, you hit it, and it rings at a certain frequency. So a tuning fork sends sound waves into the air surrounding it. The tuning fork makes one complete vibration. So one cycle, one part of that wave, one full wave. How far does that wave travel? Okay, so in this case, there's a lot of what sounds like really good options. And then the correct answer. So the correct answer, how far does that wave travel in one cycle? One wavelength. It has gone exactly one wavelength away. 340 meters. This is the speed of sound in air. This would happen if it took 1 second to make that. Or if we let a tuning fork ring for 1 second, and then how far has that wave traveled? About 340 meters. C and D, there is a mathematical equation for calculating the speed of a wave based on its density. It does not fall into AP1. I'm not even sure if it falls into AP2. But basically, this is where it's getting to here. It does depend on the square root of the air density or 1 over the square root of the air density, air pressure. Neither one is useful here. I think, and don't quote me on this because it's not AP1 material, I think the equation is inversely proportional to the square root of the density, but I'm not positive about that. In fact, you know what? Let me Google it right now. Speed of wave in air equation. Google says let's do pressure. Speed of sound. Yeah. So speed of sound, Wikipedia article. This is getting into gas laws and PV equals nRT. Yeah, there it is right there. Copy. So it depends on the inverse square root of the air density. And that's why D is wrong, because it should be air density, not air pressure. But it is inverse proportional to the square root. Not that we need to know it, but that's where that question came from. These two answers came from. Is there is math that is close to both those. But A is the right answer 100% of the time. Okay, so now on into free response questions. And I'm going to switch over to the camera so we can solve these and go from there. So these, I have 2 of these on here. A lot of the waves questions are ones that we're going to deal with when we talk about interference and harmonics and sound waves and stuff like that. So these right now are just dealing with the idea of frequency, speed, tension, that sort of stuff like that. They are not getting into the idea of doing the patterns and stuff like that. That'll be next week's sort of stuff. So some of the stuff we're just going to kind of gloss over because that's stuff we'll hit next week, and other stuff we'll go into more detail with. I'll kind of give a preview for what's coming up with that. All right, so this question is fairly old. This came out of an AP workbook, 1998, and I don't know how I got this, but this is a really old AP exam. So to demonstrate standing waves, ignore what standing waves are right now. That's not important. We'll get to that next week. One end of a string is attached to a tuning fork with a frequency of 120 hertz. So we know we have a frequency of 120 hertz for this wave. The other end of the string passes over a pulley and is connected to a suspended mass M, as shown in the figure above. The value of M is such that the standing wave pattern has 4 loops in it. Loops in quotes. So basically, you've got a wave starting here, going up and down and up and up and down and up, and then it hits here and bounces back up and down, up and down, up. 1, 2, 3, 4 loops in quotes. The length of the string from the tuning fork to the point at which the spring touches the loop is 1.2 meters, and the linear density of the string is 1 times 10 to the negative 4th kilogram meters. That looks exciting. I apologize for the autofocusing here. Focus better. Be nice. Let us see what's going on here. Let me turn on the light here for a second. Is that better? Looks like a little better. Okay, sorry about that. So we are supposed to, so we got 1.5 meters or 1.2 meters for the entire length here. And the density of the string is this value right here and remains constant throughout the experiment. That is very nice. Constant throughout the experiment means, again, it's got the point I've been harping on right now. This means velocity is a constant, that no matter what happens here, the speed of these waves will always be the same. All right, so part A, determine the wavelength of the standing wave. Okay, so for this, I may want to run to my reference tables here and say, oh, well, I remember the equation, right? I remember that lambda equals V over F. So I know what F is. F was told to us, it's 120, and I can find the wavelength from that. Well, not really. You know what? We don't know what V is. And being the good person who reads ahead on these exams, I can see very clearly that part B wants me to find V. So this is not going to be for part A, it's going to be for part B in there, because that's the part that's going to actually require us to use that equation. So if I can't use the equation to find wavelength, how can I do it? Well, there's a reason they gave us this distance here. Okay, so how many waves are there shown in this picture? Well, let's trace it. So remember, wave is an up, a down, and up. So there is one wave right there. And we can continue on doing another up. My pen is not working. Another up, down, up. This means I have 2 waves in 1.2 meters. Well, if there are 2 waves, 2 complete cycles in 1.2 meters, that means that my wavelength must be 1.2 meters divided by 2. Or in our case, 0.6 meters is our wavelength. Okay, so a lot of these questions are going to be that way. And they'll change the number of humps or the number of loops. They'll squish them, they'll spread them out. Maybe we get half of one. But the idea here is that a full wave must go up, down, and up, or down, up, down. I like up, down, up. I can remember it. I don't know why. So anyway, 2 of these, up, down, up, 1 complete cycle to this point. Then we get another one to this point. So we have 2 complete waves. We'll talk more about terminology for these things next stream when we do standing waves, nodes, anti-node, stuff like that. But right now, up, down, up, 2 waves. All right, so let's do part B now. We're looking for V. We just found the wavelength. We know the frequency. I'm going to do a little rearranging. I always recommend solving it algebraically before you plug in numbers. So this is F times the wavelength, 120 hertz. F times the wavelength, which we just found, 0.6 meters. 120 times 0.6, 72 meters per second. And there is our velocity for that wave. Okay. Now, part C says the speed of the waves along the string increases with the increasing tension in the string. Well, that's nice. So they told us very nicely that if we make the tension go up, increasing tension increases speed. So for part C, they have told us this wonderful fact that as tension increases, speed increases. Okay, good to know. We want to know, should we increase this mass or decrease it? What should we do with it to make it double the number of loops shown? So we have 4 loops here. We want to get to 8 loops. So instead of 2 waves in here, we don't want 2 waves anymore. We want to have 4 waves. That's what part C is asking us to do. What would we have to do to make 4 waves show up here? Well, let's go from this step by step. The tuning fork is always 120 hertz. Right? It's a constant value. We're not going to change the frequency. You can't change the frequency. And we want to make the wavelength get smaller. I want to fit 4 waves in this 1.2 meters, not 2 waves. So which means I need to make my wavelength go down. All right. So we know part B that the velocity of the wave depends on the frequency and the wavelength. And part C told us the velocity is directly related to the tension. So if I want a smaller wavelength, that means that I need a smaller velocity, because F is a constant. The only thing that can change here is velocity, and those two are directly related to each other. So a smaller wavelength means a smaller velocity because we have constant frequency. If we could change the tuning fork, we could do that a different way, but we can't. So smaller wavelength, smaller velocity. Smaller velocity means less tension. And since the mass, the weight of it, this mg going down there, is what's causing the tension, that means we need to have less mass. All right. So if I wanted to put that into a nice paragraph sentence, this particular exam question didn't have the paragraph response. We know the AP exam does. This is one where I would say something like, in order to make more loops, the wavelength must be decreased. Because of V equals F lambda, the only way to make the wavelength decrease lambda, is to decrease the velocity of the wave, because the frequency of the tuning fork is constant. To decrease the velocity of the wave, the tension must also be decreased, because there's a direct relationship between velocity and tension. To make the tension smaller, the weight of the block needs to be reduced, so the mass m would have to be decreased in order to make more loops on the string. And that's the kind of paragraph that I would phrase that as, going back to the basic principles: V equals F lambda, F is constant, velocity is proportional to tension because the question told us so, and tension depends on the weight of the block. And then put it all together in a nice logic paragraph going through. Okay, and the last part here, if a point on the string moves a total vertical distance of 4 centimeters during one complete cycle, what is the amplitude of the standing wave? All right, so we're looking at amplitude here, and this question is kind of tricky. But let's just draw one complete cycle of that wave. And there's my 0 line right here. So if one point on here goes up 1 meter, or goes a total of 4 centimeters, so D equals 4 centimeters here. Well, that point needs to go up, needs to come down. So there's 2 things that moved. Goes down again and comes back up to get back to the starting point. That is one complete cycle. We have moved this distance 4 times. 1, 2, 3, 4, which means the distance traveled must be the amplitude. Sorry, the amplitude is the distance traveled over 4. So my amplitude here is 1 centimeter. We went up 1 centimeter, then we came back down 1 centimeter. So we've gone 2 so far. Then we went down 1 centimeter. So there's 3, and then back up 1 to get 4. This question is kind of annoying just because we don't always think about going up and then back down. It's, oh, this distance must be 2 because you go up and then this one's staying there. No, because you go up and down and down and up, there's 4 going on there. So I would just say, be careful the way this question was phrased. Total vertical distance of 4 centimeters during one complete cycle. They're trying to trick you with that question. And just be aware of it. Be ready for it. Okay. The last question I have today is another free response one. So we will go through this one and then call it a day. So in this case, this again, the experimental part of this is something we will deal with next week and next stream, wherever streaming it, talking about harmonics and stuff like that. But this is basically one way you can figure out the speed of sound using a tube filled with water and a tuning fork, which is super cool. It's a lab I do with my AP students, and we get great results with it. It's fun to do physics with normal glasses of water and tuning forks. But anyway, we're trying to figure out the speed of sound in the air. We fill a tube with water, we put a tuning fork knowing its frequency. The tuning fork gets held over a tube filled with water until it rings the loudest possible sound it can make. And then measure this length, the length right there. And we get the data table going through here. All right, so some of this is just kind of exercise in working through stuff. So we can do that though. First one, determine the period of oscillation for each of the 5 trials and fill in the data table above. All right, so in this case, period is capital T, is 1 over the frequency. This is right off your reference tables. So really all that we have to do here is plug this in 6 times. It's not anything super difficult, I don't think. I mean, it's tedious. Don't get me wrong about that, but it's the idea is we're just looking off your reference table and we do that. So we do all those numbers. I'm just going to fill them in here, 0.0781, because I've done this already. 0.00391, 0.00347, 0.00260, 0.00234, and 0.00195. Okay, there's part A. Do the math. Okay, part B. Write an equation for the wavelength of the sound wave as a function of L. All right, so for this part, we're going to look at this corner here. And we're going to ask this little stretch of wave, this part right here, how much of a wave is that? Remember, a full cycle is up, a down, and up. That little blue part only corresponds to, well, that much. 1/4 of the wave. So the length will equal the wavelength over 4. So our answer to B, the wavelength must equal 4 times the length. Okay. Pretty simple. This is not a complicated equation. And if I were looking at this and saying, whoa, this doesn't seem like it almost seems like it's too simple, but that is it. Now, normally for an AP question like this would not be written down for extra points. This question is building us up to get some final answer, but normally this would be just something that, oh, I have to look at the picture, and the picture tells me, oh, this is 1/4 of a wave, so I multiply the length by 4, and I get the wavelength out. So that's typically what goes on there. All right, so let's fill in this chunk with 4 times that wavelength, 1.32, 1.16, 0.92, 0.76, and 0.68. Okay, so I multiplied all the lengths by 4 to get those, and then we're good. Okay, next part is to make a graph. I'm going to shoot a little bit here, and lo and behold, hey, look, I get a graph. Our spreadsheet's amazing. All right, so we've got this graphic here. It is a very nice linear graph, which is kind of awesome. And we are supposed to use this graph to determine the speed of the wave in air. All right, so well, speed is distance over time. It is also wavelength, that's the distance the wave travels over a period. And if we have this graph of wavelength on the y and period on the x, wavelength equals something times period, velocity goes in really nicely. In fact, wavelength over time, this is the slope of the graph. And that's why we had to make a best fit line. That's why we had to go through this process, because this is what's going to give us our velocity. And in fact, this is exactly what I have my kids do. And we go through and graph it. But in this case, I already have it done. Yes, thank you, Google Sheets. It is 329 meters per second. Now, again, if this is something that you were asked to do for an AP question, a lot of times this would be experimental. And you'll have to go through and say, kind of redo the wheel here. We're going to measure frequency and length. We're going to then calculate period and wavelength. We're going to then graph it, and the slope of that line should tell us the velocity. Typically how you would do the experimental design question, which again, a lot of times is sort of wave stuff lends itself really well to experimental designs, especially the water tube sort of thing. The water tube or the waves on a string sort of stuff. Very common to see that as an experimental design question on the AP exam. All right, so that brings us to the end of our stream tonight. Thank you guys for watching. And as always, check out @5volt for all your social media, figure out what comes up next and stuff like that. And just again, I'm going to throw up what's coming up next screen for all the wonderful streams. So continue checking out Monday for math and English, Tuesday for social science. Coming back in about 10 minutes to do bio, an hour for chem, and history on Thursdays. All right, thank you guys so much. Have a great night.